This is a short video on section 3-2, measures of variation. We're going to look at 3 measures of variation in this section. The first one's one we actually saw before when we were doing frequency distributions with the group frequency distribution. That's the idea of a range. Range value, the notation's in R. Very simple definition. Highest value in the data set minus the lowest value in the data set. Same as what we saw last chapter. Now the second measurement that we'll see is one that is generally only used as a stepping stone to get to the third one. And that one is the variance. And you'll see the formula for the variance on this page in the notes. The left side of the equation you'll see is sigma squared. The little o with the tail off to the right is the lowercase sigma, and then the 2 is a superscript, so that's an exponent, so that is sigma squared. And in the fraction on the right side, the numerator, we have sigma, capital sigma in this case, which means adding something up. And then inside parentheses, we have x minus mu, outside of parentheses, superscript 2, so that's a squared, and the denominator is n. So what that breaks down to, the uppercase sigma says we're adding something up. The x minus mu inside the parentheses, we saw in the last section, mu is the mean. X is each data point. So what we're doing is for each data point, we're comparing it to the mean. We're taking that distance from the mean and squaring it. And after we've added all those up, we divide by the number of data values. Now, as you'll note in the little discussion right below the formula, this is the average of the distance from the mean squared. And the reason we square it is otherwise the positives and negatives would tend to cancel out. So we don't want that to necessarily happen. By squaring it, if you take a negative times a negative, you end up with a positive. So everything is moving in a direction away from 0 by doing that. So that's why the square is involved. Now, I mentioned that the variance is basically a stepping stone typically. The more common measure, and the one we're trying to get to typically, is the standard deviation. And you'll see here in parentheses, the symbol for that is sigma. Now, the symbol for the variance was sigma squared. Symbol for standard deviation is sigma. Not surprisingly, to get the standard deviation from the variance, you take the square root. To get from standard deviation to the variance, you square it or take it times itself. Now, there's some, I mentioned some things there on page 134. I'll remind you of the rounding rule. Typically, the standard deviation, you want to show 1 decimal place more than whatever your data was. Now, a few years ago, I taught this class to a group of nurses at Conemaugh who were all preparing to go to graduate school. And when I went over this section, one of the students raised her hand and she said, "Okay, I understand the words, but what is the standard deviation?" And I kind of tried to explain the words differently, and she said, "Yeah, I hear you," but she said, I'm still missing something. And I didn't have a great answer for her at the time, so I thought about it more, and what I came up with was a kind of real world parallel. It's not a perfect parallel, but for most people it sort of helps them envision what the standard deviation does. And that relies on archery. My next door neighbor, Paul, is a hunter, and he archery hunts some years. In the years that he hunts, he makes sure that he practices before he goes out, and he is a reasonably accurate archer. So if he goes out and he shoots at a target, his group of arrows would be in a reasonably small pattern. You know, if he's aiming at a center point, he might have a 2 or 3 inch, 4 inch pattern around that center point. A friend of mine from high school, Tony, after he graduated, he got into competing around Johnstown in archery. Very good, won a lot of things, and eventually became a rep for a bow company. Now, you know, because Tony shoots a bow for a living essentially and sells bows to people, he's quite good at it. If he would shoot at the same target from the same distance as my neighbor, his arrows would tend to be closer to the center than what Paul's were, because, you know, Tony is a more accurate archer by virtue of how much he practices. You know, if you want to take that one step farther, start looking at an Olympic caliber archer. and realize, just how good those people are. As small a pattern as Tony would have, the Olympic archers would be just minimal variation from shot to shot. And that's essentially what the standard deviation is showing us. The Olympic archer would have the smallest standard deviation, the smallest distance away from the target. Tony would have the intermediate. My neighbor Paul would have the largest. I would be far larger than any of those three. If I hit the target, it would be good. But that's sort of a parallel and an explanation for what the standard deviation is showing you. Like I said, it's not a perfect thing, but for many people, it helps them envision what we're accomplishing.